Hey, this is a video about quantum electrodynamics, QED for short. This is an adaptation of the book QED by Richard Feynman. But this is a book, we don't need this. Firstly, the name quantum electrodynamics sounds very complicated. Actually, it's quite easy. You'll be able to understand it. Don't worry about the maths. Nothing's more difficult than Pythagoras. I'd first like to preface this with the fact that this is the most accurate theory in the whole of physics. So accurate, in fact, that if you had to measure the distance between New York and Los Angeles, you would have to measure the distance between the thickness of a human hair to obtain the same level of accuracy. Pretty damn accurate. QED predicts a lot of phenomena. Actually, maybe too many. Because this video series can't cover all of them. There's a lot of applications in chemistry and other fields of physics that we can't possibly cover. This is currently my favourite scientific theory, just for how accurate it is and how much it changed my perception of how the universe really works. Let's start with different frequencies, okay? Red, blue, green, that's all just different frequencies of light. The only real difference is that blue light has more energy, so it oscillates more often. You don't even need to know that. There's more colourful ones, like gamma rays and X-rays, but really we can keep it simple and just say that the red, blue and green are all we need to know. What's very important is that we treat light as particles in this theory. We're going to label those particles photons. All that means is that a photon is a particle of light. We know this. We actually know that light is divided into particles. We use a very sensitive piece of apparatus called a photomultiplier. This photomultiplier makes little ticks when light shines on it. Now if we make the light dimmer and dimmer, what happens is that those ticks stay at the same volume, but they get less frequent. This is proof that light is a particle and not a wave. Because if it were a wave, then the ticks would become quieter and quieter as you decrease the intensity of the light. If you're interested in how a photomultiplier works, go here. Okay. Essentially it's like a drummer and a violin player. When the drummer and the violin player are playing very quickly, the brightness of the light is very high, then what happens is that both of them sound continuous. As we dim the light, we hear that the drummer actually has individual taps, whereas the violin player would have gotten quieter. But since we don't see the violin, we actually see the drummer, we must conclude that photons are individual taps. Now that we have some photons, let's have some fun with them. First, let's use partial reflection. Like when you stare out a window, you see partly what's on the outside and partly a reflection of yourself. That's because some of the photons are being transmitted through the light and some of the photons are reflecting back on yourself. We'll use this scenario and explain how it works with quantum electrodynamics theory. Here's the setup. We have a light source which emits 100 photons. We have two detectors, which are photomultipliers if you will, that count the number of photons that arrive at them. These are A and B. B is inside the glass, A is above the glass. What's going to happen is that some of the photons are going to be reflected and some of them are going to be transmitted through the glass. Here are the results. 4% are reflected, arrive at A, and 96% are transmitted. Now here's a good question. How can light be partially transmitted? How does each photon make up its mind as to whether to travel into the glass? Now the answer is that nobody knows. Genuinely, there is no answer. There's no golden formula for whether an individual photon will decide to be transmitted or reflected. There is nothing like that. The only thing we know is that it has a probability of being transmitted and a probability of being reflected. There is nothing more than that. That's as deep as we can go. That's as much information as we can know. You may disagree with this. You may say, well, each photon has a special characteristic which says that if it's aimed just right at the glass, then it will be transmitted. Or if it's aimed just right, it'll be reflected. And each photon is made so that it has this special property. This doesn't work, because if this did work, then we'd be able to put lots of parallel layers of glass before the one that we are measuring. And that would filter out all these ones that have been reflected, and leave only the ones with the special property of being transmitted. But this doesn't happen. We can put as many layers of glass as we like in front of the final layer, and what happens is that we get the exact same probability of 4% being reflected and 96% transmitted. Here's the thing, if we get different results for the same circumstances, then physics and exact science is flawed, right? Well, physics hasn't collapsed yet. You can still do science, even if you're only using probabilities and not certainties. Here's the setup. Same as before, we just move B outside of the glass. Now, what you might be saying is, well, we've just got two surfaces, so we just add the probabilities. We say 4% plus 4% makes 8%. And the survey says the actual answer is it depends on the thickness of the glass. We can get up to a 16% reflection. That's 4 times what we have with single surface. And I'll explain how that works. But we'll refer to the experimental evidence. Let me get back. Okay, let's use the experimental evidence. So with really thin glass, we'll use this book as an example, we get almost a 0% reflection. Then, as you increase the thickness of the glass, you get a slightly higher percentage reflection. And so we increase it enough, and we get up to that 16% reflection. So what you might be saying is, the thicker the glass, the higher reflection. Well no, because if we increase the reflection further, we get actually a lower percentage reflection. It goes actually back down to 0%. What happens if we increase the thickness even further is that it goes back up to 16%, so it's actually oscillating. Here's the graph. This has actually been checked up to 50 meter thick glass! So our 8% prediction is actually right twice a day, like a broken clock. But the rest of the time it's pretty rubbish. So how does this work? Let's start doing some calculations. Not really. Essentially we're going to be drawing arrows on a little bit of paper. Okay, so here's an arrow. If you square the length of the arrow, you get the probability of the event happening. This is how you combine arrows. You get the tip of one arrow and add the back of the second arrow, and then you join the back of the front arrow with the front of the second arrow. Now we have 2 reflections, so we have 2 arrows, and both of those events have a probability of 4%. So we have 2 arrows which have 0.2 as their length. Here's where our simplification comes in. So we consider the many ways that the photon can get to A, and we say that it gets to A by either reflecting off the front surface or the back surface of the glass. Now, this isn't quite how it works, but it does give us the right answer, so we're going to use this for now. In maybe our 3rd video, we'll go into why this happens. Each way of getting to A has its own arrow, so the front surface reflection and the back surface reflection have 2 separate arrows, and this is where we get our results from, these 2 separate arrows combining. Time to use our imagination. Imagine we have a stopwatch with a single hand turning as the photon moves. When the photon ends up at A, we stop it. The hand finishes pointing in a certain direction. For the back surface reflection, we draw the arrow pointing in the same direction as the stopwatch, but for the front surface reflection, we reverse the direction of the final arrow. Now we have all the pieces, we can finally start using this stuff in our example. We'll start with our example. The photon leaves the source, reflects off the front surface of the glass, and ends up at A. This means that we have to reverse the direction of the arrow, which has length of 0.2. The second arrow points in essentially the same direction as the first arrow, because the glass is so thin that the difference in time is almost nothing. We end up with a final arrow which is very, very small, and then when we square this, it becomes an even smaller number. So this is where we see that almost 0 photons end up at A. As we make the glass thicker, we see that we're getting a larger and larger final arrow, until we get to a point where it's 16 and the arrows are pointing in exactly opposite directions. This is where we get our maximum value of 16%, 0.4 squared. Now we can see if the stopwatch makes an exact full turn between the first and the second arrow, then the arrows still end up pointing in the same direction. Here's where we get 0% again. When the arrows differ by a quarter turn or a 3/4 turn, then we get a right angle, and we can use Pythagoras here. A squared plus b squared equals h squared, and we can see that h squared equals 0.08, 8%. That's where we got our number from. As we can see, the first arrow always stays in the same direction, and the second arrow is always changing with thickness. This is where we get our behavior of it oscillating between 0 and 16%. And this will continue forever. Now, the technical name for these arrows is probability amplitudes, and what we're doing here is computing the probability amplitude for an event. Let's finish with one more example. When a car leaks oil on a puddle, you see this rainbow of colours. How does that work? There's just one extra rule here, which is that blue photons have a faster stopwatch than red photons. That's the only difference that we can see between the photons in quantum electrodynamics. Just the speed of the stopwatch. Now what we're going to do is we're going to simplify the puddle, or at least the light going into the puddle, into red and blue light. This just makes it so much easier to predict what's going to happen. We can think of this puddle as like a thin glass, with a top and a bottom reflective surface, and use only red and blue photons to make this thing simpler. We get this helpful graph when we do experiments. This thickness is very blue. This thickness looks a bit violet. This bit looks red, and this one looks black. As white light or sunlight is all the different colours, we get this wonderful pattern of different shades, different combinations of colours, which I can't possibly show in a video because the graph would be incredibly complicated. This phenomenon actually has a name. It's the partial reflection of white light using two different colours, and it's used by peacocks and hummingbirds, and it's called iridescence. It's pretty cool. Thanks for watching. This is the end of video 1. I hope to make this a 3-part series, so there'll be a link to the next episode there when it's out. As for now, thanks very much for watching. You've watched it all the way to the end. Great. I hope you've learned something. If you haven't, give it a dislike, but if you have, please give me a thumbs up. Subscribe if you liked it. Thank you!